So let's go ahead and take a look now at example number 2. We're going to try to see here if we could actually determine if a function like this piecewise function that we have here, f of x, is actually continuous at the number 1. Now, this is a complicated looking function. I don't know what its graph is going to really look like, nor do I really need to know in order to answer the question. Keep in mind that in order to check to see if a function is continuous at a point, I need to check the limit of the function as I move towards the value of x in question, and I need to see if it's actually equal to the y value at that point. So I'm going to calculate here two different things, and then I'm going to see if they are the same thing. So let's start here with maybe calculating the limit. Let's see how we would do this. I would say we note that we're going to need to calculate the limit as x approaches 1 for our function here, f of x. Okay, now we need to figure out how to do that. So again, it can be helpful here to at least create kind of a mock picture or a rough picture of what this function might look like. Now keep in mind right now that what this says is that I'm going to be graphing this crazy looking function thing everywhere that x is not the number 1. And then I'm going to be creating a dot or a point at 1 comma 1/2. So at 1 comma 1/2 I get this red part, and everywhere else I kind of have this blue part. Now I don't know what the blue part looks like. Maybe it forces a break apart in the graph, maybe it doesn't. But what I can see now is that if I want the limit as I approach 1, I kind of need to do the limit of the blue thing, right? The blue thing is the path that I'm moving along towards the point. So I'm going to go ahead and say that if I want the limit as I approach 1, I'm going to need to do the limit as x approaches 1 for the function x minus 1 over x squared minus 1. Oh, and this is a rational function, right? So if this is a rational function, then I should just be able to plug 1 in as long as it's in the domain, and I'll get an answer. Wait a minute. Okay, if I plug 1 in, I'm going to get 0 divided by 0, and that is not an answer to a limit. Remember, you can never state the answer to a limit as just like undefined, or 0 over 0. That's not a final value. Remember, though, if I get something like 0 over 0, I can probably simplify. So I'm going to go ahead and think about ways here I might be able to simplify what I have. And one thing that I see right away is that my denominator is a difference of squares. And so I'm going to go ahead and actually factor it into an x minus 1 and an x plus 1. That, of course, lets me see that I can easily cancel out these x minus 1s, and I'm going to be left with a limit as x approaches 1 of 1 over x plus 1. This is, again, another rational function, but now it's totally fine to plug in the value of 1 because I don't create any issues. I just end up with a final value of 1/2. Okay, so remember, my goal right now is to check the limit and the y value and see if they produce the same answer. Right now, I have 1/2 for the value on the left side. Let's see what the value on the right side would be. This here is much, much easier to calculate, though, because all we have to do now is compute f of 1. So this says, go to the function, and if x is the number 1, use this formula to tell me the y value. Okay, so that would mean that my y value is 1/2. Notice these two values actually match. So I can write this. The limit of my function as x approached 1 was actually equal to the function when I plugged 1 in. The limit was equal to the y value of the function. And so f of x is continuous at x equals 1. Notice again that in here, as I'm writing out my work, I kind of have to write some sentences, right? I have to explain what I'm doing as I'm doing it. I show the calculation of the limit, I show that I'm calculating the y value, and then I put everything together and explain why I now know that the function is continuous here.